In this video, we are going to talk about how to connect capacitors. We know what a capacitor is. We've seen what it does and how it is charged. So let me remind you what the symbol for a couple things are. This is the symbol for a battery. You will see attached to this either a voltage or a script E for EMF. If we haven't talked about that yet, we will talk about that. For this video, I'm going to stick with the V for voltage. We're going to determine that there's a pretty simple relationship between these two things. But this is a battery, a longer line and a shorter line. This is the positive terminal, that's the negative terminal. And if I'm going to take an actual electronic component, a capacitor, and hook it up to this battery, I'm going to do so by means of a wire or a line of solder on a breadboard or something, but I'm going to symbolize that with just a line, which can symbolize a wire pretty easily. Then the symbol for a capacitor looks like this. This is, you can think of it as the two parallel plates. Now there are other types of capacitors, not just parallel plate capacitors, but this is the symbol for a capacitor because parallel plates are pretty common. So let's think about some ways. If I have more than one capacitor that I'm going to put in my circuit, how are some ways I can hook up those two capacitors? Well, this one's pretty obvious. The first capacitor, I'm just going to hook directly to the terminal. We saw this when we talked about how capacitors charged. But then from the negative plate, I'm going to maybe go directly to another capacitor. So if you look at this from the perspective of the charges, and remember we're thinking about the charges as positive charges moving down the wire from the positive terminal. So one charge will move down the wire and deposit itself on this plate. When that happens, another positive charge gets kicked off this plate, right? So this one charges positively, this one charges negatively. But if you think of what that happens in the context of the other plate, say I have a positive charge moving down here, it deposits itself on this plate. Another positive charge gets kicked off here, moves down the wire. It will deposit itself on this plate, and then another positive charge will get kicked off here, move down the wire back into the battery, get pumped up, if you will, back to the positive terminal, do the whole thing again. At least that's how we think about it. Now, what actually happens in the battery is a lot more complex than that, but that's a good way to think about it if we don't care, for now, what happens actually inside the battery. All right, so notice what's happened. If I put one charge on this plate, that means I put one charge on this plate. When I put two charges on this plate, I'll put two charges on this plate. And of course, each positive charge that I put on the leftmost plates puts one equal negative charge on the rightmost plates because I'm kicking off a positive charge. So what happens is that in this arrangement, the capacitors, even though they might have different capacitances, get charged equally. This arrangement is called a series. And I think the reason for that is obvious. If the charge is flowing down the wire, you have to, if you want to think about the current, you have to go through this capacitor and then later go through this capacitor. So you go through them in a series. Now, when I say that, it sounds ridiculous because there's a gap here, right? That the charges aren't actually flowing through the capacitor, but there is current flowing here, right? Because when I put a charge here, I kick another charge off there. So there's current flowing. While these things are charging, at least, there is current flowing. And so to think about it, we think of the current flowing through the capacitor, even though we know from a physics standpoint not exactly what's happening. We think about the current flowing through this capacitor and then through this capacitor. So it's a sequential arrangement. It's a series. And what we've seen here is that the charge on each capacitor, which we usually just write as cap, make sure you can see that, yep, charge on each cap is the same. And that is a function of how they actually charge. Okay. We're going to do some more work with this, but I'm going to first introduce you to the other way of connecting capacitors. Let's put my battery here, and then I'm going to come up, and let's say that I actually put into place a split in the wire. So if I'm a charge, right, I have the choice. If I get to this junction, I can go up or I can go down. And then to those wires, I'm going to connect capacitors like this. So if you're the charge, you come out of this positive terminal, you come to this junction, you have to decide whether you go up or down. If you go up, you put yourself on this plate. If you go down, you charge on this plate. And then the charges that get kicked off, of course, are flowing here. They come back together at this junction and continue on around to the battery. So the charge has an option. That is a parallel arrangement. And the way I've drawn it, I think it looks obvious why it's called a parallel. They won't always be drawn this way. In fact, sometimes they're drawn in what can only be construed as an intentionally confusing manner. I won't do that in my classes, but it does happen. And if you look at electrical schematics, it's not intentionally confusing, but quite often the diagrams are a little hard to read. The secret to determining if something is a series or a parallel arrangement is to follow the charge. If the charge ever comes to a junction where it can either go up or down or left or right or however you have it drawn, if it has an option, that's a parallel. If it does not have an option, has to go into this capacitor, has to go into this capacitor, that's a series. All right, so what can we say about this parallel? Well, the first thing I would say is because the charge has an option, there's no guarantee that the charge on each capacitor will end up being the same. And in fact, in general, it won't be. If these capacitors have different capacitances, the charge won't be the same. But notice, I can trace a direct line from that capacitor right to the battery. From this capacitor right to the battery. What that means is that in effect, I have hooked both of these capacitors up directly to the voltage source. It doesn't matter how many wires or whatever I have in place. But what I'm saying is if I measure the voltage across these 2 points, in this case, that voltage is going to be the same as the battery voltage because there's nothing else there. If I measure the voltage across those 2 plates, put in my voltmeter here, then across these 2 points, then that is the same voltage seen by this capacitor and seen by this capacitor because I am, in effect, connecting these capacitors each directly to the battery, and that's what controls the voltage. So what I see is that the charge is not the same in parallel, but the voltage seen by each is the same. All right, so let me remind you of a few things over here. Definition of capacitance. I will put that down here. Make sure you can see that. That's the definition of capacitance. We also have, for parallel plate capacitors, this, right? We know that for parallel plate capacitors, the capacitance is a function of the physical parameters, the area of the plates and the distance between them. And then here's just the definition of capacitance. So I'm going to use this parallel plate capacitance to give you an idea of what's going to happen when I try to determine what we call the equivalent capacitance. If you're the battery, let's just do some gross personification here. If you're the battery, you don't really care that there are 2 capacitors here or 2 capacitors here. What you, quote unquote, see is that charge leaves you, deposits itself somewhere, and then comes back to you, right? You don't know or care what this arrangement is. You basically figure out that you're charging some sort of capacitor like thing, and then the charge gets back to you. So what that means is that we can determine systems which act exactly like this one, but only have 1 capacitor. We can determine a system that acts exactly like this, but with only 1 capacitor. We call that the equivalent capacitance. And in general, that makes analyzing these systems simpler. It gives us ways to do it. So let's think about what it would mean with this definition in our mind to have 2 parallel plate capacitors. Well, maybe you can see that there is, of course, a distance d between these 2 plates. Here's how I like to think about it. I like to think about this as 1 capacitor with a greater distance between the plates, right? So what I'm saying is there's some D here, there's some D here. Maybe this is D1 and this is D2. I'll write that in. This is some distance D1, this is some distance D2. When I determine some equivalent capacitance, what it's going to act like is a capacitor with a distance between the two plates of D1 plus D2. And if you in effect have made a capacitor with a greater distance between the plates. And that's just a way to think about it. But what does that do to the capacitance here? Well, if the denominator of this fraction goes up, we should expect the capacitance to go down. So what I'm saying is the equivalent capacitance of this, just by thinking about what this looks like physically, should be less than either one of these taken individually. The equivalent capacitance of this system should go down because my effective capacitor has a greater distance between the plates than either one of these. Let's think about it from the parallel standpoint. And in this case, since I'm connecting both of these to the battery, it's almost like I'm putting this plate butted up against this plate and this plate butted up against that plate. So I'm not changing the distance between the plates in this case. What I am changing is the total area of the plates. In effect, I'm making a single capacitor with an area equal to, maybe this is A1 and this is A2, right? And my equivalent capacitor will have an effective area of A1 plus A2. Well, what is that going to do to my capacitance? Well, because the area is in the numerator, an increase in area has got to equal an increase in capacitance. So what I should expect here is for my equivalent capacitance to be bigger than either one of these, right? So I can make an effective capacitor, an equivalent capacitor, with a capacitance lower than either one of these, and I can make an effective or equivalent capacitor with a capacitance greater than either one of these. Why would I do that? Why wouldn't I just buy a different capacitor? Well, the answer somewhat is economic, right? If I'm a capacitor manufacturer, I can't afford to make capacitors in every possible denomination, and that's not even a thing. So I make standards, and then I let electrical engineers cleverly design their circuits to use the available capacitors to put together in clever ways, or combinations of clever ways, to create whatever specific capacitance they need. That's one way, or that's one reason why we need to be able to do this. All right, so how's that going to work? I'm going to just give you the formulas and talk about how they satisfy the criteria we've developed. In a series, if this is some C1 and some C2, this will be some C1 and some C2. I think, yeah, you can read that. The equivalent capacitance here, the 1 over the equivalent capacitance here, let me do this, is equal to 1 over C1 plus 1 over C2 plus however many other capacitors you might have. So this is an interesting one. This is defined in terms of a ratio where the equivalent capacitance appears in the denominator. Just make sure I'm not off a frame there. I'm kind of off. This is just an ellipse. Let me move it over a little bit. There you go. However many other capacitors you have is what this stands for. So this is defined in terms of a ratio, right? So please notice, to get the equivalent capacitance, you're going to have to do this and then invert whatever you get. Because if you invert the left-hand side, you get the equivalent capacitance. You're going to have to add these together and invert them. And that will be shown in some of the example videos, which won't appear in this video, but will appear in other videos. All right, so now what is this going to do? Well, fair enough. Let's actually do a simple example to show you what happens here. If, let's say that C1 is equal to 1 farad, C2 is equal to 1 farad. We'll do a super simple example. What that means is 1 over C equivalent is equal to 1 over 1 farad plus 1 over 1 farad. Please notice the units are R in the denominator here. I think I can do this one in my head. That's 2 over 1 farads, right? And I'm going to continue to put the farads in the denominator. Now I'm going to invert these two, so it looks like C equivalent is equal to the inverse of this, 1/2 farad. And now my unit is in the numerator where it's going to have to be. So look at this, 1/2 of a farad. The equivalent capacitance is less than either of my constituent capacitances. Just like I reasoned that it had to be because of what's happening physically, right? In effect, the distance between the plates in the one equivalent capacitor is greater than these, and so the capacitance goes down. And that's what I found. So I'm happy with that. Fair enough. In the parallel, here's the way to determine the equivalent capacitance here. C equivalent is equal to C1 plus C2 plus ... right? However many other capacitors you have. You could have 2, 3, 7, 43, whatever. The equivalent capacitance is just going to be the simple summation of the capacitances that you have in this parallel loop, right? We call this a loop here. Okay, that's nice and straightforward. Let's do the same example. Let's let C1 be 1 farad, C2 be 2 farads. 1 farad plus 1 farad. Sorry, C1 is 1 farad, C2 is 1 farad. Is equal to 2 farads. No big deal, right? So I got an equivalent capacitance with I got an equivalent capacitor with a capacitance bigger than either one of my constituent capacitors, which is exactly what I said would happen. This is like connecting plates in such a way that the area of the equivalent capacitor is bigger, so we expect the capacitance to go up. Both of these will be handled in some further example videos. Of course, you can put series and parallel together in the same circuit, and then you just do this process step by step, but that hopefully will be obvious when we look at the examples in future videos. So there's really one other thing left to talk about here, which is energy. Right? Energy is stored on a capacitor, and you will find different physicists that talk about that in different ways. Some will say it's stored in the field, some will say it's stored on the charge. It doesn't really matter for the purposes of this class where it's stored. The fact is the capacitors store energy, right? There's a potential across the plates of the capacitor. If there's a potential, that means there is potential energy if you put a charge in there. So we've got to talk about this in terms of energy. We can talk about it in fields and forces. We also need to talk about it in terms of potentials and potential energies. All right, so I'm just going to give you this. This one's free. 1/2 QV, where Q, of course, is the charge on the capacitor after it's charged. Well, actually, at any point, but usually we evaluate it after it's fully charged. And this is the potential across the plates, which we know, if you have one single capacitor connected to a battery, will be the same as the battery voltage. If you have other capacitors in different arrangements, it may or may not be equal to the battery voltage, but we at least know that the total voltage available to the entire system is just the battery voltage. So whatever potential I find across the plates, that is going to be what I put in there. So this should make some sense. The potential energy has to be proportional to the charge. It also has to be proportional to the potential difference, right? If the potential difference is the potential energy per unit charge, this has to be proportional to that. Also proportional to the charge, because that's where the potential comes from in the first place. So the more charge I can put on this thing, the more potential energy I can have, right? So fair enough, that's a useful equation. However, if I remember the definition of capacitance, charge per unit voltage, I can come up with some equivalent forms of this. If I solve this equation, I basically just solved it 3 times for the different variables, and then I can substitute into this expression to get equivalent expressions. So let's substitute in for Q first. From here, I'm going to have 2 voltages and 1 capacitance, so it looks like I get 1/2 CV squared, right? I can also plug in here from here, so I'm going to have 2 charges and 1 capacitance in the denominator, So I'm going to get 1/2 Q squared over C. These are all equivalent expressions for the potential energy stored on a capacitor. Which one you use will determine on what you have available, right? If you completely characterize the system, you'll have all of these available. But if you know the charge and the voltage on a capacitor, you can find it here. If you know the capacitance and the voltage, you can find it here. If you know the charge and the capacitance, you can find it here, right?